Hello and welcome. I'm Mr. Eck and you're watching Eck Math. Today we're going to look at quadratic equations and quadratic word problems. There is a companion note sheet that goes with this, so make sure you have that. If you don't, let me know. I can get you it. Without further ado, let's get into it. A quadratic equation is defined as any polynomial of degree 2. Remember that degree is the highest exponent on a variable in that type of equation. There are three main forms of quadratic equation that you're going to see in this world. The first is called general form or polynomial form, or sometimes standard form, although standard form is used for a lot of different versions, so maybe it's best to just avoid calling things standard. But that form is where it looks like ax squared plus bx plus c. You've seen this before if you've used the quadratic formula. The second form is vertex form. This is the form that you get after you complete the square on a general form of a polynomial, and once you get it in this form, which looks like a parentheses x minus h squared plus k, then the value of vertex form is the h and k tell you the location of the vertex. It's at h comma k. Another way to think about polynomials or quadratic equations in this form is that they're transformations of y equals x squared, left and right and up and down and shifts and stretches of x squared. The third way that you might see a quadratic is factored out. So you might see it factored out into something like x minus 2 times x plus 1. And there is also sometimes a coefficient in front. So that's an example of a quadratic that's factored out. One thing about the factored out version is that those numbers at the end, they can be, of course, real numbers like 2 and 1. They could also be imaginary numbers, like you could have a quadratic that's factored out into x plus 2i and x minus 2i. And if you multiply those together using what you know about imaginaries, you could figure out what standard form or general form is of that quadratic. So those are the general forms of a quadratic, and broadly, the graph of a quadratic is a parabola. A parabola looks like this. It can open downwards. They can also open upwards. Parabolas always have the domain all real numbers, and then they have a range where one side is infinity and the other side is the y-coordinate of the vertex. And let's just make sure we understand the parts of a parabola. So on this graph, it says label the x-intercepts, y-intercepts, vertex, and axis of symmetry. Let's just pop that in and do that. The x-intercepts are where the graph intersects the x-axis, so that's, we'll say right here is an x-intercept. We'll just do x-int, we'll make that red. We'll say same here is an x-int. And one way you might also see x-intercepts in math is they are when the equation f of x is equal to 0. And another word for these then is zeros, or 0. So the 0 of the polynomial is when the y value is 0. Speaking of the y values, you can also have the y-intercept. So that's right here. Y-intercept, let's do y-int, and that happens when you plug in 0. So when x is 0, we write that as f of 0. The other feature of a quadratic or a parabola that's really nice is, of course, the vertex. And if you have this thing in vertex form, then that vertex is given by the h and k. And then the final piece of a quadratic is the axis of symmetry. Axis of symmetry. And that is the vertical line where if you folded the quadratic, the parabola from left to right, it would look the same. And the axis of symmetry always passes through the vertex. And there's one more fact about axis of symmetry that's going to be super useful in this entire section, and that is that the x-coordinate of the axis of symmetry is at x equals negative b over 2a. That's maybe the one new thing in this section, really, really useful. And in fact, let's put that fact into use right now. This problem would like us to find the vertex of this function f of x. How are we going to do that? Well, the vertex we need to find its x and y, so we're looking for a pair of coordinates. The good news is we already know all we need. The x-coordinate of the vertex is always going to lie on the axis of symmetry. So whatever this parabola is, oh, that's not the axis of symmetry. whatever this parabola is, the vertex will lie on the axis of symmetry, which we happen to know is at negative b over 2a. So the x-coordinate of the vertex, we'll say, will also going to be at negative b divided by 2a. So let's try that out. The vertex is going to have x-coordinate of negative b, which is negative 14, divided by 2a, so 2 times negative 2. Okay, so that's negative 14 over negative 4. That's going to be the same as 7 over 2, which is 3.5. So the x-coordinate of the vertex is at 3.5. Now, if we know the x-coordinate of something, we can find the y-coordinate just by plugging it into the equation. Oh my gosh, that's what the equation's for. So we would write that the y-coordinate is found by plugging in the x-coordinate, but mathematically we would write that we're doing f of negative b over 2a, or in this case, f of 3.5. I'm going to do this on a calculator and come back to you in a second with the answer. All right, I just plugged it in because there was some decimals, and calculator says that the y-coordinate is 12.5. So we'll say f of 3.5 is 12.5. We just got that by plugging in. So the vertex is going to lie at 3.5 and 12.5. That's it. Let's look at the next problem. It's similar, but a little bit different. This question says, find any relative maxima or minima of 3x squared plus 6x plus 5. If you feel like it, give this problem a try. Pause the video, and then come back and see if you got it right. All right, before we get too excited, let's fill in the bottom of this note because it helps to know what we're looking for. Are we looking for a maximum or are we looking for a minimum? And the thing that tells us that is the number in front of the x squared term. That's our a value. If a is positive, we're looking at a parabola that looks like this. That is, the parabola opens upwards. I'll just say up. And if the parabola opens upwards, this is going to have a relative minimum. On the other hand, if that a value is negative, then you're looking at a parabola that opens downwards. It doesn't have to be at the origin. It could look like that. And then your parabola would have a relative maximum. So in this case, a is 3. So we are looking for, we know this opens up, and that we're going to be looking for a minimum. And we're not actually looking for a maximum. Okay, well, the minimum or maximum is just the location of the vertex. So let's just find the location of the vertex again. The x-coordinate is given by negative b over 2a. So that's going to be negative 6 over 3 times 2, which is just negative 1. We can then plug in negative 1. And so it's just 3 times negative 1 squared plus 6 times negative 1 plus 5. So that's going to be 3 minus 6 plus 5, also known as 2. Now, let's make sure we state our minimum correctly. So we're going to say that this has a minimum of 2 because the minimum is the y value, and we're going to say it happens at x equals negative 1. And that'd be the kind of the correct way to approach this. We can double check our answer by going to the y equals menu in our calculator, typing in the equation, and pressing graph. And indeed, we have a minimum of 2, and it happens at x equals negative 1. So all this works out just right. You might be wondering, hey, why does the vertex and axis of symmetry occur at x equals negative b over 2a? Why does that happen? Well, it all comes back to the quadratic formula, and you can write this down. You don't have to know exactly why it is. You just have to know that it is this. But if you were curious, remember that the quadratic formula tells you that the zeros of any quadratic, that is the x-intercepts here in red, happen at x equals negative b plus or minus this thing, square root of b squared minus 4ac, all over 2a. Huh. But another thing that we've learned in our class is that if you have a fraction and you have a single term on the bottom, but you have two terms on the top separated with a plus, like addition or subtraction, or a plus or minus in this case, you can split that fraction up. And then you can see that the zeros actually occur at x equals negative b over 2a plus or minus this thing over 2a. And that means that the two zeros the two x-intercepts, we should say, are negative b over 2a plus this thing over 2a and negative b over 2a minus this thing over 2a. And look at the axis of symmetry. It's at the midpoint of the zeros. The axis of symmetry is at the middle of the zeros. Well, what number is at the middle of those zeros? Well, if you add them up, these terms will cancel out, and then if you divide by 2, what do you get? You'll get negative b over 2a. So it's kind of saying like, hey, here's the axis of symmetry, and then the square root of b squared minus 4ac over 2a is the distance from the axis of symmetry to the x-intercept. And then the negative distance is the leftward one. So that's why negative b over 2a gives you that axis of symmetry. Here's some other tricks you can do with quadratics. So say we had a problem that wanted us to write a quadratic equation with zeros at x equals negative 3 and x equals 7. And also they maybe gave us a clue about some specific values the function should go through. Well, it may not seem like this is enough information, but actually it is. And the key idea is that we're going to use something called the factor theorem. The factor theorem says that if x equals c is a zero of any polynomial, then x minus c is a factor in that polynomial's equation. Just some fun facts about the factor theorem. This isn't limited to quadratics. It works with any polynomial. And technically, c can be real or imaginary. Now, today we're lucky we have two real zeros. Actually, we have integer zeros, so it's super nice. But that means that our quadratic equation could be y equals x minus 3, that's our first zero, times x minus 7. Now, this isn't quite done. Let's first turn this x minus 3 into x plus 3. X minus minus, the same as x plus. And, oh, there's an x. Let's multiply it all together. So that's going to be x squared minus 7x plus 3x minus 21. All right, now this might work. We'll say y equals, but here's the thing. 2 zeros is not enough information to guarantee a single quadratic. Because if all we said were that the zeros were at negative 3 and positive 7, there's an infinite number of quadratics you could draw. You could draw one like this. Whoa, not like that. You could draw one like that. You could draw one like this. You could draw one like this. You could draw a really steep one like this. There's an infinite number of quadratics, and so what you need is one additional value anywhere on the curve, and that will lock you into having only one single quadratic. And here's how you use that value. If you look up at the top, ooh, not like that. If you look up at the top, the factored form of a quadratic has two factors, but it also has a possible leading coefficient. And we use the letter a for that possible leading coefficient, so we're going to do the same thing here. We're going to say that our real equation has y equals a x plus 3, x minus 7, or a x squared minus 4x plus 21. And we're going to solve for that coefficient and figure out what it is. And how are we going to do that? Well, we're going to plug in 1. So since we are told that f of 1 is equal to 12, then when x is 1, y should be 12. So what we can do is say 12 equals a, and then we can plug 1 into this equation. So 1 squared is 1, minus 4, plus 21. So 12 equals A times 21, 18. Is that correct? I'm going to stop here for a second and notice that I've made a little mistake. I wonder if you noticed it. I found out because I was thinking about when I plugging 1 into this version, and I noticed if I plug 1 in here, I would get negative 21. But here I was getting positive 21. That's because 3 times negative 7 is negative 21. And I just even had it and I copied it down wrong. So things can happen to everyone. We're just going to fix it right here. So we're going to make that a negative. We're going to make this a negative. And then when we plug in 1, it's going to be 1 minus 4 minus 21, which is negative 24. And then we can divide by negative 24. So 12 over negative 24 is equal to A. That means negative 1/2 would be our A value. And then we are finally ready to write our equation back. Now, instead of multiplying this negative 1/2 in, that's not really going to help anything. So I'm just going to write it using the factored form. F of x equals negative 1/2, x plus 3, x minus 7, which, usually you want these things factored anyway because that's what helps you graph it. But this is how you use the zeros of a quadratic and the leading coefficient and a point to find the equation of a quadratic through any 3 points. Technically, if you had any 3 points, you can find a quadratic. It's a lot easier when 2 of those points are the zeros. If you don't have the zeros, you have to do some system solving. It's much more difficult, but in this case, at least, it's pretty nice and easy. Just make sure you plug that x value that's given back in and let you solve for the coefficients. So in addition to all these problems from Mathland, we can use quadratic equations and what we now know about them to solve problems from real life, or at least problems that feel like they could sort of exist in real life. So on the back here, we have a projectile motion problem. It's fall right now, at least out here, so we are imagining that there's a pumpkin catapult that launches a pumpkin into an empty field. The path of that pumpkin is given by the following quadratic equation. So we can imagine that the catapult is maybe placed at the origin right here, and the initial value we can see is 8 when x is 0, so from a height of 8 feet, the pumpkin is going to go up and then down, and it's going to reach some distance, and this is our x, and this is our y, and this is just a picture of that pumpkin's path. All right, so the first question is, how far away from the catapult does the pumpkin land if nothing were in the way? Well, if we, again, kind of looking at the graph and we imagine the situation, the pumpkin lands when y equals 0. So to solve this, we could set the equation equal to 0. 0 equals 0.0, negative in front, 5 x squared plus a little 2x plus 8. And we could try to solve. Now, we could try to factor this, we could do all this fun stuff, but we have a big gross decimal in front, so it's probably easiest to go to the quadratic formula, and we can do most of it by hand, and we'll do the final step in our calculator. So we're going to get x equals negative b, so that's negative 2, plus or minus the square root of b squared, so that's 4 minus 4 times negative 0.05 times 8, and then over 2a, so that's going to be negative, we'll just say 2 times negative 0.05. I mean, I know that's going to be negative 0.01. All right, let's go to the calculator and type that in and see what we get. All right, now I typed this in a calculator. You can't do plus or minus. You can only do one thing, and I typed in the plus. And I got something a little surprising. I got the answer as x equals negative 3.66 feet. Now, what the heck is that telling us? Well, the quadratic formula doesn't know that we are doing a problem about a pumpkin catapult. It just says, hey, boss, here's the zeros. And if you imagine this parabola, hey, if you extend it backwards, it's going to intercept at negative 3.6. That's not the answer we want. So counterintuitively, the plus answer from the calculator or from the quadratic formula actually gives us the wrong answer. but it's easy to fix. We can just arrow up, tab back in. This is one nice thing about doing it in the fraction template, is you really can just switch the sign, hit enter again, and you get the correct answer, which is about 43.66 feet. So this happens right there. X equals 43.66 feet. Sorry, does this say yards? So, yards. If you've ever seen these pumpkin catapults, they're really big. They shoot things a long way. So 43 yards seems pretty reasonable. So we'll write that, 43.6 yards. Okay, next question. What is the maximum height that the pumpkin achieves? Oh, now how can we attack this? Well, let's think carefully about parabolas again. The maximum height occurs at the vertex. This is the point of maximum height, and so really what we're looking for is the relative maximum of this equation. So what can we do? Well, we can find the location of the vertex by doing negative b over 2a. So for problem b, here we'll do it like this. We can do negative b over 2a. In this case, that's going to be negative 2 over 2 times negative 0.05. So let's type that in and figure out what it is. All right, so we typed that in the fraction template, and we did negative 2 over 0.01, and we got, I guess, unsurprisingly, 20. So this happens at x equals 20, and then to find the height, we have to plug it in. So we have to do f of 20. You can just plug that in the equation. I want to show you a calculator trick while we're here. Oh, not like that. If you go to your y equals and type in the equation, I did it already a little bit, and then you go home, you can do second quit. If you go second y var, so that's alpha f4, and you get y1. Notice how y1 is highlighted. That's because there's, well, that's the default. And then you can do y1 of 20. That's going to take 20 and plug it into the equation in your y1. So y1 of 20 is 28. So f of 20 must be 28. And that means that the maximum height, what is the maximum height the pumpkin achieves? 28 yards. That's pretty high. The last question is saying, 40 yards away, there's a 10-yard tall tree. Would the pumpkin actually hit the tree? So instead of being in an empty field, we're imagining there's a tree out there now. Let's go back to the picture and maybe draw the tree in. So 40 yards is like close over here. So we're saying maybe there's a big tree right here. Maybe it's a little pine tree. And it's 10 yards tall. So is the pumpkin going to hit the tree? Well, really all we need to do is compare the height of the pumpkin at x equals 40 to the height of the tree at x equals 40, which we know is 10. So really to do problem C, all we need to compute is f of 40. And conveniently, on our calculator, because we plugged the equation in, we're ready to plug anything in. We can just go back to y1, and instead of doing y1 of 20, we can do y1 of 40. And it tells us that at 40 yards away, the pumpkin is at 8 feet tall. So if the pumpkin is at 8 feet and the tree is 10 feet, yes, since f of 40 is 8 yards, yards, not feet. Since f of 40 is 8 yards, the pumpkin will hit a 10-yard tall tree. And that's how you tackle a projectile motion problem. Nothing in here is particularly complicated. It's really more about decoding each question and understanding what do I need to do with the quadratic equation that I'm given in order to answer the question. So that's, it comes easier with practice, but it's worth just taking your time to make sure you understand the units and whether it's asking for X or Y and exactly what it's asking for. And then it never hurts to, of course, answer every question in a sentence. Let's look at another type of quadratic word problem. This is one where you might be trying to maximize an area given some constraint. So the story here is that you have 300 inches of tape to mark out a play area for your cute stuffed animals. And you would like the area to look like the picture. Maybe you want to have a dividing line down the middle. Every version of this problem may have a slightly different picture that you have to work with. In the past, you've maybe done problems like this where you just have a rectangular area, and you may remember from the past that it's actually the best, most optimum area is when your play area is a square, or your area you're fencing in is a square. But the addition of this extra line is going to change that. So it's not automatically just going to be that a square is the best again. So anyway, how are we going to attack this? They've asked for the dimensions that will give a maximum play area, and what is the maximum area you can enclose. So it's important to think about the function we're trying to maximize. We're trying to maximize an area. And we need to then write the area function. But we can't write the area function without labeling some things in the diagram. So then you go back to your diagram, or draw the diagram if it's given in a book. Let's label some stuff. Let's label one of these long segments x. It doesn't matter which one is x and which one is y. Now you might be tempted to label these little segments y. I think it's going to be easier if you always label the longer pieces as much as possible. So let's label the long side y. Then our area function, we can say the area is a function of x and y, and it's just x times y. Now we have a problem because we technically right now have three variables. We have a, x, and y. We don't know how to solve that or graph that or do anything with it. So the next step after we label this up is to try to get rid of one of these variables. We're basically going to try to get y in terms of x. So step 1 is write your area function. Step 2 is get y in terms of x. That's our goal. Let's go to the diagram. Let's label some more stuff. So this is x. That's also an x. That's also an x. And this long length here is also a y. And this is where we can start to use our constraint. We've been told we have 300 inches of tape, so we can write the equation 300 is equal to 3x plus 2y. Now, we want to get one of these variables alone. Honestly, it doesn't matter which one, but it's usually just easier for our brains to handle if we solve here for x's, and that means that I want to get y alone. So let's solve this one for y. So we're going to say 300 minus 3x equals 2y. And then we can say 300 minus 3x over 2 is y. We can leave this as 300 minus 3x over 2. Or we could split the fraction and make this 150 minus 3 halves x equals y. It doesn't really matter. I'm going to use the second one. Now, why do we want to do that? Because in step 3, we want to substitute back in our information from our constraint. So now we have our area that's just in terms of x. This is like function notation, not multiplying by x, is equal to x times 150 minus 3 over 2x. That's still representing the area. We just replace this y with this 150 minus 3 halves x that we got from solving the constraint. And let's go one further. Let's multiply this x back in. That would be 150x minus 3 halves x squared. And maybe let's put that x squared in front. Negative 3 halves x squared plus 150x. And I'll call that a of x, our area function in terms of x. Why do we care about that? Why did I get it in that form? Well, because what are we trying to do? We want to maximize the area. And what did we just make? A parabola or a quadratic that represents the area. So we can think about this as a parabola with a negative leading coefficient, so it's opening downwards in some way. X is x, and the vertical axis, it would be the area. So what do we need to find? We need to find the vertex of the parabola. It's actually the same as the last 3 or 4 problems we've done. We're just trying to find the vertex of this thing. So that's our last step. Where are we going to put it? Step 4 over here. Find the vertex of your area function. So that happens when x equals negative b over 2a. Okay, so negative b is negative 150, and we have to divide by 2 times negative 3 halves. This is a situation we could do a calculator, we could do a complex fraction, but these 2's are going to cancel out, and so it's going to be negative 150 thirds, negative thirds, and that's the same as 50. So when x equals 50, the area will be maximized. So we'll have 50, 50, 50. Now's a good time. We could come back and say that if we had 300 inches of tape, what were the other things? Well, we know that y is 150 minus 3 halves x, or we could just come back in here and we could say 300 equals, sorry, I lost my eraser, equals 150 plus 2y, so 150 must equal 2y, and 75 must equal y. And that means that the final area, so we'll say step 5, is answer the question. Area equals, and this time we just go back to our original function, length times width, 50 times 75. Or 3,750 square inches. Do make sure you include the correct units. If we're doing an area, our answers should come in units squared, and since we were talking about inches of tape, we're going to answer all that all together. So this problem is not too bad, but one thing that's confusing is you have 3 variables. You have the area, the x, and the y, and the vertex you're finding is not a vertex with x and y, it's a vertex with x and area. So just make sure you kind of know what you're looking at. Oh, by the way, another way that we could have, once we got x equals 50, another way we could have found 3750 is gone into our area function. We could have done negative 3 halves times 50 squared plus 150 times 50. That also would give us the same answer. So you can find the final answer by using your area function and plugging in, or you can find y and then just multiply it. I think that's a little more concrete. That's how I usually approach it. One more last kind of problem. So we've been kind of doing some real world problems. We can also use quadratics to approach some sort of mathy problems. So here's one that goes like this. Of all the numbers whose difference is 12, find 2 numbers whose product is as small as possible. What is this product? And I want to challenge you something. You can do this problem, if you've been watching this video carefully, with everything that you know. So pause the video and try this. Come up with a claim. Come up with 2 numbers whose difference is 12 and see what their product is. See if you can get the smallest thing. So pause now and come back when you have an answer. Are you back? Do you have an answer? Well, in that case, let's look at how we're going to solve this problem. You might have initially said, oh, let's just take a problem and explore it. So numbers whose difference is 12. So that means they're 12 apart. So an example might be 2 and 14. And then 2 times 14 is 28. Maybe that's the smallest. Maybe. What about 1 and 13? Well, we certainly know that 1 times 13 is just 13. Hey, could that be the smallest? Yeah, it could be. Now, if you're being really careful, you might have noticed that actually numbers don't have to be positive integers. So what about 0 and 12? Then that product is 0. That's pretty small, but is it the smallest? No, it is not. Because what if your number had been negative 2 and 10? Then your product is negative 20. And negative 20 is smaller than 0. Sorry to say. So this is a situation where thinking about numbers and remembering that numbers can be positive or negative actually gives you kind of the best answer. Now, you may from here have a guess at what our two numbers are, but we're going to prove it. We're going to be really mathematical and actually try to prove what our numbers are. So let's call the two numbers x and y. And since there's nothing special about x or y, let's assume that x is the larger of the two. You could assume that y is larger of the two, but it's nice to assume that because then we can write that x minus y equals 12. Then what we might do is we might solve this for y, and we might say, okay, then x minus 12 equals y. Now, why are we going to do this? Well, remember up here, we had to get we had our two dimensions, x and y, and we had a relationship that we solved for y, and we plugged into some other function, the area function. Well, here, what are we trying to optimize? We're trying to optimize the product. So we need a product function. The product function, we'll say P is going to be x times y. But we already know that y is x minus 12. So our product function, really, we could write as a product function of x is x times x minus 12. Hey, that's x squared minus 12x. And let's, again, carefully think about what we're looking at here. This is going to be a parabola. This time it's a parabola opening upwards. Probably something like this, where this is x, and this is the product of x times y. And we're looking for the minimum, which means that, yet again, we're looking for the vertex. So we can find the vertex at negative b over 2a. So that's going to be 12 over 2. Oh my gosh, it's 6. And that's x. That's actual x. We also want to know y. Well, we know y is x minus 12. So 6 minus 12 is negative 6. And then what's the product of x and y? Well, x times y is 6 times negative 6, which is negative 36. And so what might we say to summarize our answer? I would say something like the minimum product is negative 36 when x equals 6 and y equals negative 6. And so again, it's just a use of quadratics. Hardest part of this problem is understanding what it's asking for and just getting the equations written down in the first place. But once you get that, it's just a little vertex action, negative b over 2a. And this is one where it does kind of show up that there's a balance, that the best set of numbers is when the values are equal. But you can't always assume that. You do need to prove it out every time to show that you've minimized the quadratic, because you could come up with some way where maybe it's not always the same. All right, folks, that's it for this video. Thank you all for watching. I will see you in class, and I'll see you next time. Goodbye.